Introduction. It's evening. Dev and Mohan returned home after shopping. Mohan switches on the fan and bulb. As he saw that two bulbs are on, he switches off one bulb. Dev was watching this carefully and thinking of something. Then Dev said to Mohan that when you switch on the bulb, it doesn't glow instantly. And also, when you switch off the bulb, it doesn't diminish instantly. What is the reason behind that? Mohan told him that it is due to the induction of current. The induced current always tries to oppose the course of change. When bulb turns on, then an induced current develops such that it tries to remain off. Similarly, when bulb turns off, then an induced current develops such that it tries to remain on. That's why the bulb doesn't glow and diminish instantly. Students, electromagnetic induction is everywhere around us. We use many appliances or applications that are based on it. So today we'll study about the electromagnetic induction. Objectives. At the end of this lesson, you'll be able to define electromagnetic induction, understand the experiments of Faraday and Henry, define magnetic flux, understand Faraday's law of induction, state Lenz's law and conservation of energy, define motional electromotive force and energy consideration, define eddy currents, calculate mutual inductance and self-inductance, describe AC generator. Definition. In our everyday life, electromagnetic induction plays a vital role. Transformer, generator, train, and telephone are some examples which work on the principle of electromagnetic induction. An electric current can be produced in a circuit by a changing magnetic field. The current in the coil brought about by a changing magnetic field is called an induced current and is said to be set up by an induced EMF in the coil. The phenomenon of producing an induced EMF with the help of a magnetic field is called electromagnetic induction. The experiments of Faraday and Henry. Experiment 1. Consider a bar magnet that can slide back and forth along the axis of a helical coil of wire to which a galvanometer is connected. When the magnet is at rest, no current is observed in the coil. The magnetic field at the coil is not changing. When the magnet moves towards the coil, a current flows in the coil. As the magnet approaches, the magnetic field produced by it at the location of the coil increases. When the magnet moves away from the coil, a current is again produced, but in the opposite direction. The magnetic field at the coil decreases. We conclude that only relative motion between the magnet and the coil is required to produce the current. Experiment 2. Consider two coaxial coils, one called the primary coil P, connected to a battery via a key K, and the other called the secondary coil S, connected to a galvanometer. When the key is closed, the galvanometer in the secondary circuit deflects momentarily and then returns to zero. The magnetic field at the secondary coil increases from 0 to a steady value. When the key is opened, the galvanometer deflects momentarily in the opposite direction and again returns to 0. The magnetic field at secondary coil decreases from the steady value to 0. The galvanometer reaches 0 when there is a steady current in P. Here the magnetic field at the secondary coil is not changing. Magnetic flux. It is a measure of the quantity of magnetism, being the total number of magnetic lines of force passing through a specified area in a magnetic field. If a uniform magnetic field B acts perpendicular to the plane surface, then the magnetic flux through the area A is given by the product of B and A. If the magnetic field B makes an angle theta with the normal to the surface, then the magnetic flux is given by BA cos theta. Or it can be written as phi is equal to dot product of B and A. Magnetic flux linked with a closed surface may be defined as the product of the surface area and the normal component of the magnetic field acting on that area. Faraday's law of induction. Faraday summarized the results of his experiments in the following two laws. Whenever the magnetic flux through a circuit changes, an EMF is induced in the circuit, and it lasts only as long as the change in flux is taking place. The instantaneous EMF induced in a circuit is equal to the time rate of change of magnetic flux through a surface enclosed by that circuit. E is equal to minus differentiation of phi b with respect to t. The negative sign is introduced to indicate the direction of the induced EMF. The induced EMF always in the opposite direction of change in magnetic flux. If a coil of wire consists of n loops, each with the same area, then the flux through all loops is given by minus n differentiation of phi b with respect to t. Example. Let's take an example on Faraday's laws of induction. The magnetic flux through a coil perpendicular to its plane and directed into the paper is changing according to the relation. Phi is equal to 5t square plus 10t plus 3 meter Weber. Calculate the EMF induced in the loop at t, which is equal to 5 seconds. Let's see the solution. Given phi is equal to 5t square plus 10t plus 3 meter Weber, it can be written as phi is equal to 5t square plus 10t plus 3 multiplied by 10 raised to the power minus 3 Weber. We know that E is equal to d phi by dt. By putting the values in this equation we get E is equal to t plus 1 multiplied by 10 raised to the power minus 2 volt. Now substituting the value of t as 5 seconds, we get E as 0.06 volt. Hence the EMF induced in the loop at t is equal to 5 seconds is 0.06 volt. Lenz's law and conservation of energy. Lenz's law states that the direction of the induced EMF or induced current is such that it opposes the change that is producing it. When the magnet is pushed towards the coil, the induced current produced will oppose the push of the magnet by creating a north pole on the face of the coil near the magnet. When the magnet is pulled away from the coil, the induced current produced will oppose the pull of the magnet by creating a south pole on the face of the coil near the magnet. According to Lenz's law, the induced EMF opposes the change that produces it. We perform mechanical work in causing the change in magnetic flux. So, it is the mechanical energy which is converted into electrical energy. Thus, Lenz's law is in accordance with the law of conservation of energy. Motional electromotive force. Let us consider a straight conductor moving in a uniform and time-independent magnetic field. Let a rectangular conductor PQRS, in which the conductor PQ is free to move. The rod PQ is moved with a constant velocity v. It is placed in a uniform magnetic field B, which is perpendicular to the plane of this system. If the length RQ is x and RS is L, the magnetic flux phi b enclosed by the loop PQRS is equal to BLX, but x is changing with time. So the rate of change of flux will induce an EMF given by minus differentiation of BLX with respect to time, which is equal to BLV. The induced EMF BLV is called motional EMF. So we can produce induced EMF by moving a conductor inside uniform magnetic field. Energy consideration. Let R be the resistance of movable arm PQ of the rectangular conductor. The overall resistance of the rectangular loop is R, and this does not change as PQ is moved. The current I in the loop is given by E divided by R, which is equal to BLV divided by R. The force exerted on the arm PQ due to magnetic field is given by ILB, which is equal to the product of B square, L square, and V divided by R. Power required to push the arm PQ with a constant speed V is given by product of B square, L square, and V square divided by R. Thus, mechanical energy which was needed to move the arm PQ is converted into electrical energy and then to thermal energy. Eddy currents. Eddy current is defined as currents induced in a thick conductor when the conductor is placed in a changing magnetic field. Consider a conductor placed in a continuously changing magnetic field. Due to the continuous change of magnetic flux linked with the conductor, induced currents will be set up in the body of the conductor itself. These currents assume a circular path and their direction is given by Lenz's law. Eddy currents are used to advantage in certain applications like electromagnetic damping, induction furnace, magnetic braking in trains, electric power meters. Assessment. Before proceeding further, let us know how much you have learned. Drag and drop the correct option. Mutual inductance. The phenomenon in which a changing current in one circuit induces an EMF in another circuit is called mutual induction. Let us consider two long coaxial solenoids, each of length L. The inner solenoid S1 is of radius R1 with N1 turns per unit length, while the outer solenoid S2 has radius R2 with N2 turns per unit length. B1 is equal to product of mu naught N1 and I1. The magnetic flux through a single turn of S2 is given by mu naught N1 pi R1 square I1. The magnetic flux linkages solenoid S2 having a total number of N2L turns is given by mu naught N1 N2L pi R1 square I1. M21 of circuit 2 with respect to circuit 1 is given by mu naught N1 N2 L pi R1 square. Similarly, we calculate the value of M12 and is given by mu naught N1 N2 L pi R1 square. From above two equations, we can say that M12 is equal to M21, which equals M. And the value of M is given by mu naught N1 N2 L pi R1 square. Self-inductance. The phenomenon in which a changing current in a circuit induces an EMF in the same circuit is called as self-induction. According to Lenz's law, the EMF of self-induction always opposes any change in the current in the circuit and hence is generally termed as the back EMF. The total magnetic flux passing through a coil is proportional to the magnetic field, which in turn is proportional to the current I in the coil. Phi equals product of L and I. Here the proportionality constant L is called the self-inductance. According to Faraday's law, the induced EMF in the coil is given by minus L di by dt. Let us consider a long solenoid of cross-sectional area A and length L having N turns per unit length. Current I flow through the solenoid. The magnetic field set up inside the solenoid is given by the product of mu naught N and I. The magnetic flux through one turn of the solenoid is given by the product of mu naught N, I and A. The flux linkage in the solenoid with the total number of NL turns is given by mu naught N square ALI. Hence, the self-inductance of the solenoid is given by mu naught N square AL. AC generator. The AC generator is an important practical device that operates on the principle of electromagnetic induction. It converts mechanical energy into electrical energy. It consists of a coil of wire that is mechanically rotated by some external means in a uniform magnetic field. As the coil rotates, the magnetic flux through it changes with time, inducing an EMF and a current in an external circuit. The ends of the coil are connected to the external circuit by means of slip rings that rotate with the coil. Each ring slides against a stationary carbon brush to which the external circuit is connected. The magnetic flux through a single turn of the coil at any time t is given by dot product of B and A, which is equal to BA cos theta. It can also be written as BA cos omega t. Here omega is the angular velocity and theta is the angle between the magnetic field vector and area vector. If the coil consists of n turns, the magnetic flux linkage in the coil is given by NBA cos omega t. According to Faraday's law, the induced EMF in the rotating coil is given by NBA omega sin omega t. or it can be written as E is equal to Em sine omega t, where Em is equal to NBA omega is the maximum value of the EMF. The induced EMF varies sinusoidally with time. Did you know? If the magnet is rotated about its axis, there is no change of magnetic flux linked with the loop and hence no EMF will induce. In dithermy process, we make use of eddy currents for the localized heating of tissues in human body. In coin-operated vending machines, eddy currents are used to detect counterfeit coins. Summary. Let us summarize what we have learned. The phenomenon of producing an induced EMF with the help of a magnetic field is called electromagnetic induction. Only relative motion between the magnet and the coil is required to produce the current. Magnetic flux is a measure of the quantity of magnetism, being the total number of magnetic lines of force passing through a specified area in a magnetic field. Lenz's law states that the direction of the induced EMF or induced current is such that it opposes the change that is producing it. Induced EMF can also be produced by moving a conductor inside a uniform magnetic field. Eddy current is defined as currents induced in a thick conductor when the conductor is placed in a changing magnetic field. The phenomenon in which a changing current in one circuit induces an EMF in another circuit is called mutual induction. The phenomenon in which a changing current in a circuit induces an EMF in the same circuit is called as self-induction. AC generator operates on the principle of electromagnetic induction. It converts mechanical energy into electrical energy.